Okay, so yes, today we are going to extend, if you want, the set A that we have defined before. So this is the set of all almost regular germs. And to the right of 0. Okay. And so what we're going to construct an algebra of germs plus that contains. Like we saw that A is not closed under addition. That contains A. All right. So and so when you do this, we briefly mentioned, right? The problem is, in order to get an algebra, I kind of have to drop that assumption about the Dirac series that it always starts with this constant term, C0 times the power of e to the minus x. And if I drop that, but I still want to compose or log compose at infinity, then I find higher iterates of log after that, or x. Log x. So the idea is that we are going to try to do that and just deal with the extra iterates of log that appear. But when you do that, one thing that happens very quickly is that the order type of the support of your series is not going to be omega anymore. It's going to become omega squared. So the first thing I should do is make sense of what I mean by asymptotic expansion when the order type is bigger than omega. Okay, so how do we make sense of asymptotic expansion? Okay, so when the order type is like in all the classical notions of asymptotic expansions, the series, the monomials, are always terms of functions. So when you subtract the truncation of a series with order type omega, you're subtracting actually finite sum of such terms, which makes sense as a function. You use that to define asymptotic expansion. When the order type of your support is bigger than omega, well, you will get to a point in the support where there's an accumulation. So where the truncation has infinite support, and then just knowing that each of the monomials defines a function doesn't mean the infinite sum does. And in our case, right, we have these Dirac series that are divergent. So you can't do. There's no canonical way of defining asymptotic expansion. So here's the setting, right, where we can do this. So I'm still going to work with monomials that are themselves functions or germs of functions. Okay. So let G be a multiplicative group. Think of this as the monomials for my series. And it's a subgroup of a Hardy field. I think by now everybody knows what the Hardy field in terms of functions is, right? So I don't have to define that again. H, okay, at plus infinity. I mean, right, powers of x, powers of e to the x are all such examples, okay? In general, it's just a multiplicative subgroup that I use for my space set of monomials. And then I write, as usual, R double parentheses G for the Transseries ring, or just the generalized series ring in the sense of. And so generalized series field, those are just all formal sums with real coefficients and elements in G, multiplying elements in G, okay? With the property that since G is a subset of a Hardy field like plus infinity, property has to be that the support of such a series has to be anti-well in the ordering of the Hardy field, reverse value. Okay, so right, usually you talk about powers of something, and then you look at the exponent, and everything goes the other way, the ordering. But if you just look at it in terms of monomials being elements of the Hardy field at infinity, the big ones are the ones that are dominant. So you need reverse well ordering. Express usual thing. Okay, so I want to say what it means somehow to have a series like this as an asymptotic expansion. Okay, so for that I need maybe one more thing. I want to assume something else about G is a scale, which means I don't have monomials that are equivalent to each other, right? Meaning that the set G is linearly ordered by the dominance relation. The dominance relation on Hardy fields. Okay, so that means, right, once I have made that assumption about the monomials, that suggests I should be able to use them to express asymptotic expansion. Okay, but still, how do I get past the problem of accumulation points in the support? I have to relativize the notion to a given algebra of functions. Okay? And I do this the following way.
Trick?
So,
a trick?
K be an algebra. So by algebra, I usually mean real algebra. Okay. An algebra of terms at plus infinity. So T a map of this algebra into this generalized series field. And I want this to be an algebra homomorphism. Okay, so what matters here is really this K that matters, the T matters, and the set of monomials matters. So I'm defining triple K T. That's a terrible term, but doesn't matter. I just write QAA for quasi-analytic asymptotic algebra. So this is three assumptions, right, which I kind of need to make sense of asymptotic expansion. First of all, T has to be injective, so this whole thing has to be a quasi-analytic algebra. In order to be able to talk about asymptotic expansions, I need to truncate my series, right? So, and in order to be able to assign a function to each truncation, right now sometimes truncations may have infinite support, I need the truncations to be in the image of T as well. So the image T of K has to be truncation closed. With these two things in place, I can now say that what I mean by asymptotic expansion, I want to say that that T of F is the asymptotic expansion of F. The following sense. So for every F in K, every term in K, every monomial G in G, if I take F and I subtract, well, I want to truncate series F, series of F, right, at the monomial G. So this is, I said that before, right? This means truncation series TF. At G. Meaning I only keep the portion that's above the monomial G. So truncate that, but now that's just another series. So that's not a germ of a function yet. But it is in the image of T. And since T is injective, there's exactly one germ in my algebra K that's associated to it. Can the audience hear us? Hear
Hi, Patrick, can you hear me?
Now I can hear you. I could not hear you.
No, I just had a small question. Do you require G to be a full set of representatives for the Archimedean classes?
No.
Okay.
No.
Might be smaller than that.
I mean, for what?
For your field K, for your RD field H. Sorry.
No, I don't know. I don't know anything like that.
Okay.
So I don't, and you'll see I don't require that. But I'm not trying to recover H here. Mm-hmm. Anyway, if you subtract the germ associated to the truncation about G of the series TF, that's dominated by G. Okay.
No, you have to take T again, right? Because F is not in K, right?
Yeah, exactly. So is that, and so is this. Oh, I do have to say one thing. Yes, G should be in K. See, G should be in K. Okay. Yeah. I keep forgetting to say that. Yes, the monomial should be there. Okay, so then this extends the usual notion of asymptotic expansion. Well, it does if you have familiar monomials and finite support that the pre-image is the usual function you associate to that.
So you extend the dominance relation to K, right?
Yeah, it does, right? With this definition, it does happen. Yes, that's what the condition makes. But it's not linearly ordering K. Mm-hmm. Okay, I mean, the dominance relation for germs of functions is always defined. It's just maybe not always true. Mm-hmm. So what we're saying is that the germs in K are related to each other with, in this way.
Sorry, Patrick.
Yes.
I can't quite see what you wrote up there on the screen because it's not visible. But is it not that you want that T of G to be in K? Sorry, that you want G to be in T of K. Sorry. On the monomial, the image in RG. T of K, and then you need the inverse of G.
Yeah.
On the right hand side.
T minus 1 of G.
Yeah.
Should be K or something like that.
Well, okay, G can be in both, right?
I mean, it just depends. Yeah. But
yeah, I mean, I want to.
so you want G to live inside, sorry, K to live inside R of G?
Yeah, I mean, that's the thing, right? The monomials are actually germs in this setting, this setup. So I guess I want I want T to map the germs to themselves. Okay.
Thank you.
That makes sense? Yeah, that's what I'd like. All right. Any other questions? Okay, so so far so good, right? It's just a definition. What are examples of such? Well, any, you can take the analytic germs at plus infinity. So real analytic germs. No, sorry. Here, yes, it's all done at plus infinity. The real analytic germs. Plus infinity. Okay. Or more generally, real meromorphic germs at plus infinity. In that case, you even have a field. And there, of course, the power series, right, are the usual power series in 1 over x, convergent power series in 1 over x, and the monomials are just powers of x. So that's familiar, a little less familiar, right? But I will get back to that anyways. The Hardy field of R and X has an embedding into the transseries. And what is G in that case? Well, we can take as G all trans monomials, right? That would be perfect. Okay, I'm not saying that. Oh no, I can't. So G has to be a subset. Okay, so yeah. So I'm going to explain. Say a word about this. We will see this again, so I don't want to explain too much. So the monomials here are the so-called convergent transmonomials. And I will define that next week. It's the set of convergent transmonomials. So they define terms of functions in an obvious way. Okay. T is the map that, right, this one is due to Vandenries, McIntyre, and Barker, and they define this T in the paper. And one of the papers where they study RNAs. Okay. So that's another example. And they actually show that it satisfies this kind of condition. All right, so there are certainly examples around. Of course, the almost regular germs, that set is not an algebra, so it's not an example. Okay, so now what I would like to do is, right, I want to construct such an algebra, QA algebra that contains A, or at least contains A composed with e to the minus C. To translate it to logarithmic term. So, a bit more specifically now, right? We're going to construct QA algebra F that contains almost regular terms in the logarithmic term. Okay. All right, and I want to use the uniqueness principle that we discussed. Okay, so if I want to use the uniqueness principle, right, that means I have to not just work with real function germs like the almost regular ones. I have to talk about germs of functions on standard quadratic domains. Okay. So that means I need to adjust my definition of scale a little bit. It means in particular that whatever monomials I'm going to use still forms a scale on not just the real line at infinity, but standard quadratic domains. Okay, so all right. So G is a strong scale. If every monomial, or the element of G, has a holomorphic, continuation on every standard quadratic domain. It might be enough to do it on just at least one, but I'm just going to say the examples are going to satisfy that. On every standard quadratic domain, omega yeah, what do I mean by scale? Right. So to say that the dominance relation linearly orders G, like the set of all these germs, means that when you have two distinct germs, one dominates the other, which we in analysis express as one being little o of the other in the domain in question. And so that has to happen such that if G1 and G2 are distinct terms in my monomials, right? Then either G1 is little o, so no, I should put it's G1 of Z now is little o of G2 of Z as the real part of Z goes to plus infinity in omega, or the other way around. In other words, these monomials make sense to talk about asymptotic expansions of the entire standard quadratic domain. Okay, so we have examples of such G's. Well, kinds of things that appear in Dulac series, right? Because that's what I want to. If I fulfill my goal, I don't know that it's going to be happening. Okay, so if G is the set, actually no, I don't want to call that G. Right? L set all products log -1 to some power alpha 1 times log 0 to some power alpha -1 alpha 0 up to some iterative log. Okay. So well, log -1 is x, right? Log 0 is x, and so on. Where k integer greater than or equal to -1, and the alphas are real numbers. Positive for negative. Okay. So then the cell is not just the group under multi, right? It's not just a multiplicative group, it's a multiplicative R vector space. L is a multiplicative vector space. It is certainly a scale, and that's just calculus as real terms, okay? But in fact, it's a scale on every standard quadratic domain. L is a strong scale. On standard quadratic domains. That's actually an important observation, right? That explains why we're working on standard quadratic domains to begin with. I mean, why don't we just work with the extensions to the half plane, for example? Why not extending to half planes? Okay, and that's because on half planes, right, powers of e to the z, or say, let's say just e to the minus z on a half plane does not uniformly go to 0 as the real part of c goes. Well, as the real part, yes, but so yes, but
Z times
sorry,
Z times e to the power minus z.
that's right. Yes, there we go. Right. Right. E to the z, no, e to the minus z still has the property that as the real part goes to infinity, you go to 0 uniformly. Okay, but z times e to the minus z does not. Okay, does not go to 0 uniformly in the real part of z as z goes to infinity in the right hand, right? So that's a monomial. That means you can use this kind of thing to show that L is not the scale on the right half plane, for example. Okay, so we need something that is not quite the right half plane. So, of course, why not take proper subsectors? Why not only extend to proper subsectors? By proper subsectors, I mean a sector of opening less than pi over 2. Okay. Well, in that case, right? So now we're talking about something like that. A little exaggerated, I guess. Right? That would be a little exaggerated. And the problem here is that we don't have our uniqueness principle on these sets. Okay. So UP fails. In fact, counterexample is just, let's say if the opening of this thing is alpha, which is a bit less than pi over 2, right? You can take, which one can I take? Take. Beta is, I think, what am I trying to say? I'm trying to find something that contradicts a function that's not 0, but that is less.
Something like exponential to the minus x to the power.
Yeah. So right, but beta is what? Just a little bit less than 1, I guess. Yeah, that's enough, right? So if beta is, but it has to be a little bigger than something else. So it's a bit less than 1, but bigger than pi over 2 minus alpha, I guess. Right?
Cosines of the sample, right? It's the cosines of.
Yeah, right. So if beta is between these two, then I'm good. Yeah. Then, well, e to the minus c beta, right? That is still going to be little o of e to the minus rho z. For every rho greater than 0, that's the condition for a uniqueness principle. And it's bounded on the sector. And it's bounded on the sector S, but it's not 0. So that shows that this principle does not work on sectors. Okay. So we need something between sectors and half planes, and standard quadratic domains are such domains. Okay. Where both work. Uniqueness principle works, which makes it, but it has to be big enough for that. But we still have a strong scale here with these monomials. For that, we need something less than half. Okay, does that make sense? Okay. So that's, now everything is taken care of. Right? So what we're going to do now, right, we're just going to do this construction inductively. So we start by constructing something a bit simpler than the They're almost regular germs in the first step. So step 0. Let A0 be the set of all terms at infinity that have a bounded holomorphic extension or continuation on some standard quadratic domain. It might depend on the germ. Okay. And what else do I want? And for which there exists a series. This is a bit simpler than a Dulac series, right? There are only exponentials. There are no polynomials in front. So there's a series f of x. So what is that? That's really a generalized power series in one variable, which usually write like that, composed with e to the minus x. Okay. And I want, again, here, like in the case of almost regular germs, I want the exponents to actually go to infinity. So order type omega. And what we call that natural support. Starting point is that natural support. Okay. So for series with natural support, I can still use the old-fashioned asymptotic relation. So I'm assuming such that the f of the germ f of z should be minus the truncation of the series at some monomial. What should I write for monomial? I'm just going to write it out. Okay? So this guy here is infinity ai e to the minus alpha I x. Okay. So if I make a truncation 0 to n, then I actually here I have a germ of a function in the obvious way. These are all germs of functions. Okay. This is going to be the log of e to the minus alpha n. See, here this is to be in the domain omega. Okay. So the asymptotic relation here has to hold on omega. And again, the fact that these monomials form a scale on omega, all this actually makes sense. Okay, so what can we say about this now? It's not hard to see. I'm not making any special assumptions about the coefficients anymore. Right? Other than they're all real numbers. Okay. And so this is actually an algebra, a set AZ. Okay. And in a way, in fact, this is a subset of A, because we have no polynomials anyway. So every one of these starts with a constant coefficient. Okay. And when you compose them or log compose them, you get another one of these. So, but this is an algebra, it's just a sub-algebra. things we're interested in. All right, so now I said that I want to make this more interesting. So I want to repeat this construction now by replacing the constant coefficients with something that I've already constructed. Okay? Unfortunately, I can't replace the constant coefficients in this whole setup here just by the germs I constructed or I obtained in A0. Why not? Because those coefficients grow of similar size as the monomials themselves, e to the minus z monomials. So I can't do that. But what I can do is, right. I can even say I'm running out of time here. I'll finish these things next time. But T0, right? So this series here, I want to call T0 of F. Okay. So the fact that we have asymptotic expansion means the series is uniquely determined. There are not two possibilities. That's the first thing. Right. So T0 is actually a map. And this T0 is injective because of the uniqueness principle. Right? Same as in the almost regular case. So this goes in here. No, that's not how you write it. Real multiplicative vector space generated by e to the z. Okay. This is injective. That's why I use the unique space. Okay. And that's why I need this whole asymptotic expansion stuff to happen on standard quadratic domains. Okay. So we can extend it. We can extend A0 to a field. Fraction field F0. Which means, there will be germs in there that go off to infinity now, and that start with a positive power of e to the z, whose expansion starts with a positive power of e to the z. Okay, so let me just give me 5 more minutes. I do have 5. So step 1, right? What I'm going to do next, I'm going to change e to the x to x by putting log in from the right. Okay, so I'm going to call f prime 1. It's going to be my f0 that I there it is. And you compose with log on the right. Slow it down, all down. Okay. So now this guy here, right, everything has an asymptotic expansion in terms of powers of x, which means the germs in here grow polynomially. Okay. So everything in here, all germs are polynomially bound. Still a field, right? When you plug in something in the right, you don't change that. Now the asymptotic expansions are just power series, generalized power series, or Laurent series, if you want. And but what does this do about, right? What's the domain definition of these things? As if you look at them as holomorphic functions. And so take a germ in here, look at its holomorphic extension to a standard quadratic domain. Now I plug in log from the right. What's the new domain of definition? well, it's much bigger, right? The logarithm collapses things. Logarithm, he maps the right half plane where to a strip. Okay. And as a germ of a set over here, right, this strip is contained in every standard quadratic domain. Which means the logarithm, like if I plug in logarithm on the right, all these terms in F11 are still defined at least on standard quadratic domain. So it's defined in even bigger sets. Right? So each term is defined on every standard quadratic domain, at least in the sense of germ. Okay. So I can use these guys now as coefficients. Let's do the same construction again. But they grow much slower at plus infinity than the powers of e to the minus c or e to the c, because they're polynomial. So step one, I could just start all over again with the same idea that A1 be the set of all terms, for which there exists a series, but now the series does not have coefficients, real coefficients anymore, but it has coefficients in my F11, F1 prime there. Everything else is the same monomials, right? But the coefficients are now germs of functions for the moment. They're not quite series, right, like I said before. And now, right, that means the AIs here, they now depend on Z as well, but they are of polynomial growth. So this all still makes sense. Okay, so that's my condition as an asymptotic expansion. So I still want these series here that I'm allowing to have natural support in this monomial. Okay. So, okay, I get again an algebra. But this time it's not contained in A anymore because it contains it. Why does it contain A? Well, because each of these coefficients, right, they can be polynomials in 1 over Z or in Z. That's a special case of such AIs. So now it contains all the almost regular terms, but in fact a lot more, because these guys here can have infinite support. Their series can have infinite support too. So right now I can define let's call this now S1. This S1 is still injected by the unique expansion. Because if you have a series like that, where all the coefficients are 0, then by the uniqueness principle, they still have to be 0. Okay, so define T1 of F. So that's my S1 of F. This is going to be the sum. I goes from 0 to infinity, e to the minus alpha I z, right? But I replace AI of C by the asymptotic expansion that it has, which was, oh, did I even say what that was? Here, right? T1 prime of a term here, and a term like this is going to be f composed with log. It's just going to be t1 by t0 of f composed with log as a series. That's the obvious way to do it. With that in mind, right, that's what I'm going to use here, t1 prime of a now. Now each guy here has order type omega, right, which means in general t1 of f will have order type omega squared. And now you can check, and this is just an exercise now, that A1 with this L as monomials, right, so it's only part of that, and T1. This is a QA algebra. Oh, it didn't say that for A0. Yes, this is a QA algebra. Okay. So now we've already constructed one that contains A, okay, but is actually an algebra. But we can keep going. There's nothing that stops us. Right? I can do the same thing again now. Go to the fraction field, push in log from the right, use that as coefficients, start again to define A2. Now we'll have end up with series that have powers of e to the z times powers of x or z times powers of log z, and so on. You can keep going and exhaust the whole thing. So yeah, I'll stop here because I'm running out of time. You can mull over this construction a bit. I will try to say a couple more things about it, and then see where to go from there. Any questions?
Can you show the board with T1 prime again?
Oh, T1 prime is just T0 composed of log. Right. Right. I mean, that makes sense. If you plug in log on the right for the functions, then for the asymptotic expansion, you also have to plug in log on the right. But as a Transseries, this of course makes sense. Okay. But so yes, at each step of the construction, right, I'm still using the notion of asymptotic expansion, the traditional notion of asymptotic expansion. I have a natural support series, but the coefficients are terms of functions in this case. So I can still talk about asymptotic expansion in this sense, right, without referring to anything background. But then after the fact, when you go to the last step, you'll find that making this replacement actually produces a QA algebra. So when you truncate this series here, at any point, you have something that you can subtract from it. So that the image is truncation closed and so on. You can subtract something to show that it acts as an asymptotic expansion in the sense of the definition.
So in this first step from T0 to T1, you're using the fact that the monomers are again linear order, right? So
yeah. So right. So all the monomials are in this L that we checked before. And L contains all the monomials that appear in this construction.
okay, the L from the L from the
all the roots of log are there. Right?
F and X. F and
L log and X, yes. All the roots of log and X are there. Yeah. Well, okay, no, I think I only said the iterates up from -1 to infinity of log are there. But you could also enlarge the whole thing and take just all the group generated by all iterates of log, positive and negative. And it's still a scale. Okay. Oh no, it's not true. No, I'm wrong. It's not a scale on standard quadratic domains. You have to stop at -1. For -2 or anything that below that, it's not good. Yeah, e to the z is not good on standard quadratic domain. It's too big. It's too fast. Yeah. Doesn't work anymore. Right? Yeah, so it's yeah. You can only L is exactly like I defined it, right? So here, what's now? No, I did not write it. No, it was on here. But here, it's right here.
So just take a part of this asymptotic scale to extend to the quadratic domain. You cannot take all monomials. Just
No, you can't. No, not all monomials generated by iterates of x or log. Right. So you can only the biggest one is that's allowed is e to the minus z on standard quadratic domains. E to the e. No, e to the z is not allowed. Right, so log -2 does not work anymore on standard quadratic domains.
But in what you read, you start with log -1 still there.
Yeah, log -1, that's where we start. And here, that's exactly what we do. Log -1 is always the dominant one in this construction, and all the others are going to be higher iterates of log. So it always stays in that L. The monomial ring is in that L. Yeah, and that's actually. But these questions are extremely important for what I want to do next. Right. What I want to do next is, can we do this with other monomials coming from Rnx, not just the iterates of log? If so, which ones? Okay,